Our next speaker is Prof Simon Garrington, who's coming from the Jodrell Bank Observatory, and today he's going to talk to us about RASOR and plans for a new UK facility for radio astronomy, space weather, and space situational awareness.
Okay, thanks very much, and thank you for the opportunity to talk to you today. I'm Simon Garrington, University of Manchester, Jodrell Bank, and this talk is about our plans for RASOR, a new UK facility for radio astronomy, space weather, and space situational awareness. This is a collaboration between universities of Bath, Birmingham, Manchester, Oxford, and also SDFC RAL Space. And the principals are Mike Garrett in Manchester, Mario Bizzi here at RAL Space, and Marco Martorella in Birmingham. So RASOR addresses, we think, what are strategic needs for a dual-use UK capability in three key areas: high resolution and rapid response radio astronomy. High resolution because this will be a complement to square kilometre array. That would be a fantastic survey instrument, but it won't really deliver the high resolution to answer some of the key questions. And rapid response because we've just heard how Rubin and facilities like that are going to transform our view of the dynamic sky. We need rapid response facilities to follow those things up at all wavelengths. And that little figure shows an example of both. That's the emerging jet seen at high resolution in the radio from the neutron star merger, first seen in gravitational waves. Secondly, dedicated space weather monitoring capabilities distributed across the UK for understanding and prediction of adverse space weather events and their impacts on the Earth. And then finally, but importantly, diverse space situational awareness capabilities, sovereign capabilities in the UK to protect assets, key assets in space, and understand threats and debris. Oops. That's not going forward. Let's click down here. Okay, all right, sorry for that. Okay, so the RASOR concept will build on existing UK expertise, investment and infrastructure. We'll add 10 new SKA-style dishes to the existing e-MERLIN array and 4 low-fire arrays to the existing capability in Chilbolton. Correlation and processing will happen at Jodrell Bank and also at REL. These locations are still to be decided, but these will extend across the entire UK, and we'll be looking for locations where we can stimulate engagement with these facilities and also sort of grow skills locally. So we're aiming for a maximum extent of 800 kilometres across the UK. That is 10 times the extent and resolution of the SKA, and similar to the best resolution that we can get from the ground from new facilities like the Extremely Large Telescope. We're aiming for low-cost, low-energy operations integrated with SKA data processing, European capabilities, and feeding data into Met Office, NSPOC, and so on. So before I get into some of the applications, just want to stress that RASOR is fully aligned with all those strategic comments that we heard about in the first talks this morning. Space strategies, both on the civil side and on the defence side and security side, and also with wider industrial strategies. Don't need to tell this audience about the importance of space, importance of protecting key assets at GEO, and the risks to some of those key assets at GEO. But some of those common themes include investing in space domain awareness, building on existing UK capabilities, expanding dual-use sensor networks, ensuring the wider benefits of sort of cross-domain civil military research. And RASOR will do all of these. We're equally well aligned with strategies on the science side, with the SDFC and space weather roadmaps. I think RASOR can address at least 13 of the 23 key frontier science questions that SGSC have, and many of those require high angular resolution beyond, say, what SKA can do. I just put down some of the numbers here. SKA mid frequency array at the moment will extend across about 36 kilometers. RASOR is at least 10 or 20 times that, to 500, 800 kilometers, so much higher resolution, half an arc second or third of an arc second for SKA, 20 milliarc seconds for RASOR. This has been put forward as a proposal for UKRI infrastructure funding. It's been through all the SDFC panels, but given the current funding uncertainty, we're still waiting to see how best to proceed with that. We set this up in two phases. The first phase would install a first dish on a site we've already identified in North Wales. It's Spaceport Snowdonia. It's important that we demonstrate that we can efficiently and effectively install these dishes, commission them, and connect them to our existing infrastructure. And even that first dish will have immediate benefits for e-MERLIN in terms of science and our space situation awareness capabilities. And then we want to optimize the other locations across the UK, look at the trade-offs between cost, performance, the extent of local support, connectivity to the network, and so on. And then there'll be a scalable deployment phase. We can scale this according to the number of antennas we want to install. Let's look at some of the science. One of the key science questions is, how do planets form around young stars? This is a key question for SKA2, but I think we really need that additional resolution that larger arrays like RASOR could bring. Somehow we need to go from the dust that ALMA sees around young stars to the planets like we have in our own solar system and that JWST is now seeing. So we know that dust sticks together chemically. We know that large boulders will cling together by their own gravity. But in between, in the pebble scale, at a centimeter scale, that's rather fragile. So we really need to observe and understand that centimeter scale. And we're doing that with e-MERLIN now. Fantastic results from Jane Greaves at Cardiff, just starting to detect this centimeter-sized material in planet-forming systems. So to see centimeter-sized stuff, you need centimeter wavelengths, and if you want to get the resolution to see terrestrial orbits around in the nearest star-forming regions, then you need baselines of hundreds of kilometers, and that's exactly what RASOR will deliver. We can simulate the sort of imaging quality that we can get. So here's a sort of toy model of a planet-forming system. We can this is our current array, so you can just sort of see something but really struggling. And then as you add those other antennas across the UK, you see everything. So that's the sort of detail we're aiming for. You can go further, and we do this all the time. We add together telescopes across Europe, and you can see even more detail. I'm going to skip through the next few fairly quickly, but there are many other astrophysical applications, especially in the formation of galaxies. And just to say that to understand the physics, you need to disentangle the different emission mechanisms, and that means high resolution at a range of wavelengths. And at the longer wavelengths, it's just lambda over d, you need longer baselines to do that. Some of these images, I think, speak for themselves. Fantastic e-MERLIN imaging of the starburst galaxy M82. And like Rubin, we're going back and we keep observing this, and all these objects are changing. So the supernova remnants fade, new things appear, and one of the new things just spotted in a paper just coming out now is one of the best candidates for an intermediate mass black hole, about 2,500 solar mass black hole on the edge of M82. This is a fantastic radio image just published, just out in Nature this month. So the optical, this is a gravitational lens. The thing in the middle is the foreground galaxy lensing what's behind it into this Einstein ring. Keck optical images, the grayscale, the radio image from a global network of telescopes, this superb colored overlay on top. And that is so good that when you zoom right in, that tiny pinch point is revealing a 1 million solar mass clump of dark matter that's just making that tiny distortion. Absolutely superb result. So on the space situation and awareness side, through a NATO research task group, the the RASOR partners, so that's mostly me at Jodrell and Marco Martorella in Birmingham, working with MIT and Lincoln Lab, have really pioneered the use of using large sensitive radio telescopes as the receivers in bistatic radar configurations. So we use transmitters in the US, Germany, here in the UK, as the transmitters, and we use these large telescopes as receivers. And by doing that, we can increase the sensitivity by a factor of 30. So we pair the largest radio telescopes, so Jodrell Bank, still the third largest antenna in the world. We pair that with the most powerful space radars, 3 megawatt transmitter at Haystack in the US, and in principle we can get down to centimeter-sized objects at GEO. So I think that's really important. We can make precise range and range rate measurements, so precisions of meters, millimeters per second in range rate, microns per second squared in range acceleration. We can make long coherent integrations to get the sensitivity. And for tumbling objects, we can image those using Doppler tomography or ISAR image techniques and getting down to meter resolution at MEO and GEO. Just in the last year, we've made further significant steps, first by static detection of debris in GEO orbit, for example, showing how we can use lower power transmitters, so just a communications transmitter on the Goonhilly antenna paired with the Lovell telescope. We can do things in GEO even with lower power transmitters. And a separate strand of work using the DSN transmitter in Madrid to do near-Earth asteroids. So these 100-meter class objects at about twice the distance of the Moon. Some fantastic results on there. And some of that work done by one of our students, Phoebe Ryder, who's here moving amongst you today, will be buttonholing you for the Jodcast, so your opportunity to get on the country's longest-running astrophysics podcast. But to really make it clear the sort of potential advantages of these techniques, we're being funded by the UK Space Agency to do a live real-time demo, hopefully at High Wycombe, where in real time we sort of take control of the Lovell telescope, move from a science target to objects in GEO, see that radio echo in real time, and then continue to do the detection, characterization, and imaging in real time. I think that will hopefully have a real impact on the operational side for these capabilities. What else can RASOR add in this area? I think one of the key things we want to be able to do is relative positions in 3D of objects in close proximity at GEO. Understand why that might be useful. Optically, you get information in the sky plane. Radar gives you the range and rate. You can fuse those together. We are doing combined experiments at the moment with our optical colleagues, but it's a challenge when these objects are close together in proximity. And I think what we can do with RASOR is use differential long baseline measurements to we're aiming for sort of 10-meter precision, relative precision of objects in GEO proximity. And that's possible because these networks are existing network and RASOR in future are synchronized across the country at the picosecond level. So we're able to make these very precise measurements. That is already done for objects further away. So on using global combinations of telescopes, we can make these precise trajectory measurements, including JUICE, and I think these measurements will play a key role in reconstructing the orbits of Jupiter's moons for JUICE, and that tells us about tidal dissipation and evolution. And we're building new receivers now, so that the UK can take a key part in those measurements for JUICE in the next few years. On the space weather side, then absolutely central to RASOR are dedicated space weather capabilities tailored to the UK's needs, distributed across the UK. The UK, expertise is unrivaled here, especially here at RAL, and it's RAL Space and Bath that are leading this part of the project. And this slide aims to capture some of the basic ideas and the range of radio techniques which are used to study the sun, the heliosphere and the ionosphere, by observing scintillation of distant sources, by cross-correlating that scintillation to get velocity measurements, by using dispersion and Faraday rotation of pulsars to get both densities and magnetic fields. And that combination of density and magnetic field is the sort of holy grail of space weather measurements, because it's the magnetic field that couples those things to the Earth. Here's an example from just a couple of weeks ago. Colleagues here at RAL Space, Richard Fallows and Mario Bizzi, they're taking advantage of full-time access to the Chilbolton LOFAR station while the LOFAR upgrade is happening to make these measurements. And they're working directly with the UK Met Office to show how those measurements can be fed into operational space weather forecasting that we'll hear about later. And then also on the ionosphere, then the combination of then these sort of measurements can provide much better information about ionospheric disturbances and understanding the impact of those. So I'll just finish up. So I think we have a fantastic opportunity and a need to develop an integrated sovereign UK radio infrastructure supporting space science, space safety and security. I think we can leverage existing UK expertise, investment and infrastructure to deliver what would be a world-leading facility for high-resolution radio imaging with wide-ranging astrophysics and cosmology cases, a dedicated UK capability for space weather research and prediction, and a unique long baseline synchronized coherent network for space situational awareness. RASOR will be a very powerful capability in terms of resolution, agility and sensitivity, be fully complementary to SKA and optical space situational awareness, and fully aligned with all the strategic comments that we've heard about this morning. Thank you.
Thank you very much. Do we have any questions in the room?
Hello. Yeah, I have one question that recently I heard in a conference that these ground-based telescopes of radios are affected by the radio interference. So the network which you're showing, how is it mitigating those interference for the observation?
It is a challenge. It's a challenge because we want to observe wide bandwidths and only a small fraction of the spectrum is protected for science, whether that's radio astronomy or Earth observation. One of the advantages of a long baseline network is that the local terrestrial interference is then not correlated between the different antennas. So what we're doing is, with a network of telescopes, we do a cross correlation of those, and it's that cross correlation that then generates the radio image. So you have a much better mitigation when you're operating networks of telescopes rather than single antennas. And there's a discrimination based on the sort of fringe rate and phase rotation rate even for objects in space generating radio interference compared to the target observation you're looking at. So I would say that these large networks have some degree of mitigation that individual antennas don't have.
Great, thank you. I think we have time for one more question.
Hi, over here. Thanks very much for the presentation. I guess for the SSA application, you can at best see a third of the geo circle.
Yep.
Is that operationally actually still attractive, or what would be a concept for going global?
So we are working with global partners in that experiment. So also we're working with CSIRO in Australia using transmitters at the Kwajalein site for those longitudes. So yeah, we're certainly looking at this. The NATO research task group includes many partners across Europe, includes the US, and also partners in Australia as well. So it's a global endeavour for sure.
Okay, great. Thank you very much. So I think sure that you'll join me in thanking our session 2 speakers.